So hello everyone, this video is to present a paper accepted at the European Conference on Software Architecture 2020. And the title of the paper is VisArch, Visualization of Performance-Based Architecture Refactorings. I'm Katia Trubiani and I will show my co-authors in a map. As you can see, our main challenge was about the time zone, because we have Poyan in US, Andre and Sam in Germany and Austria, I'm in Italy, and Alda and Sarah in Australia. So it was very crazy to organize our calls. But let's go to the core of the paper. So with this paper, we are reasoning about the performance of software architecture. So the idea is that you have a software architectural model, a set of performance requirements, and then a set of performance analysis results. What you may discover is that the performance analysis results are not fulfilling the performance requirements. Like, for example, the system response time is larger than 10 seconds. And then the key question is what to do. We can modify the software architectural models in order to have some design alternatives and hopefully improve the performance of the system. The main problem is that modifying architectural model is not easy. And to support this task, we were using performance antipatterns. Why performance antipatterns? Because performance antipattern, they basically have in their specification, the specification of the problem and of the solution. So they are about what to do and how to solve the performance problems. However, performance antipatterns, there might be several options. The ones that we were using in our case study are listed in the slide. Specifically, we have the circuitous treasurant, concurrent processing system, blob, extensive processing, and MPT semi-track. But in a case study, we found 64, so they are really a lot, they are many. There is another cross-cutting concern that will be presented by Alda.
Hi, everyone. As Katia mentioned, there's another issue that we have to deal with, and that has to do with uncertainty. At the architectural level, there are a lot of parameters that we do not know what their actual values will be when the system is implemented, such as, for example, what is the number of users that will use the software system, or what are the software system operations that will be used when the system is implemented, or processor and disk requests needs, or for instance, what are the processor, disk, and network latencies. So all these uncertain parameters may affect performance. So one issue that we have to deal with is how to handle uncertainties. One possible solution that we investigated in previous work was to use polynomial chaos expansion, which is a work published at JSS last year. And with this work, we tried to understand how the distribution of performance will be when we consider different uncertain parameters as an input. So let's go to our next slide. The goal of this work is to guarantee that the system is robust given a set of uncertain parameters. Robustness, the way we consider robustness is similar to nature. It's about the ability for tolerating perturbations. So the system needs to be robust. Its performance needs to be robust with respect to these uncertain parameters. Our research question that we aim to address with this work is how can we use visualization to help identify refactorings that improve performance?
Hello, everybody. Katia and Alda nicely motivated the work. I'm going to say something about our approach, the methodology that we follow. So we start with some specific performance requirements that is specified by a software architect. And then we have some estimation about the performance metrics using the technique that Alda mentioned. And the key here is to exploit uncertainty in the estimation about performance and be able to reason about performance requirement violation in a more systematic way. Our solution is to have a repertoire of different refactoring that can address these performance issues that we find out in the system. And the key technique that we exploit in this work is basically this visualization about the architecture, antipatterns, and the refactoring that can be done in a automated fashion. So here is a snapshot of how this visualization looks like. So in each row, you see different refactoring solution, and as a column, you see some distribution about different performance metrics, for example, throughput, runtime, and so on. So basically, this visualization helped the architect to reason about performance through the uncertainty of these performance estimation.
Hello. So we applied our example or the visualizations to an example, which was a case study from a previous paper. It's an e-commerce system, and particularly we used model-based evaluation, performance evaluations with layered queuing networks for this system, for which the architectural model or an excerpt of it is displayed here. So in particular, we looked at 6 different architectural refactorings and at different performance metrics, particularly the throughput and response times of 2 of the components. And then we fed this data into the visualization that's presented and explored what we can find out based on the visualizations about the refactorings and their impact on performance.
So, hi everyone. The visualization is lots of different colors. The first are particularly important, the first 6, they show the different performance-based architectural refactorings from red, purple, brown, pink, olive, teal. They're down on the left-hand side on these squares underneath. And we also use 2 different blues and 2 different greens to represent these metrics for response time and throughput for the browse catalog and purchase product metrics are the results they're shown in the distribution below. So we loaded all the data into a lineup, and this video shows all the information, all the data that we have. So on the left-hand side, we see our combinations of refactorings, and then we have our 4 columns we just described. You can hover over the individual box plots to see the data, like the max, min, median, for example. Then we have 4 different columns which indicate each of our refactorings just for ease of manipulation and sorting. And on the right-hand side, we have an overview. This first row is the program without any refactoring at all. And this is the results of that run. And then below that is all the different runs. We can sort through our results and actually start to look at the patterns that we see. Unfortunately, we have so many results that it's hard to see in this visualization. So we have this option to concatenate all the information and make this, this visually really compact. And we can see all these colors at once, and we can start to see some patterns from our data. What was an interesting pattern that we found was that when we ran the blob and applied blob, all the different throughput and response time for the BC were very different when we had blob applied and when we didn't. And we also found that as we start to explore the data, we could apply multiple criteria to our sorting. So for example, when blob was applied, but also EST was applied, we can see that the results also showed some real differences. So over on our metrics, we can see the distributions are quite different than when those 2 refactorings are not applied. We can also reorder the ordering of that criteria, the sorting, and we can see 4 very different combinations appearing on the screen.
So to conclude, in this talk, we presented a new visualization to better understand performance-based architectural refactorings. And with the paper, we also share all the data, which means the results of the model solving with all the performance evaluation results, all the models, and also the visualization itself. And as a future work, we plan to do some user studies to understand better how they like or what they just don't like about the visualization, how it supports them. And based on that, we would like to tweak the visualization, use different or maybe additional visualization techniques, and of course, apply this to a larger case study.
Thank you, everybody.
Thank you.
Thank you.
Thank you. Thanks for watching.